Good afternoon, everyone. Thank you very much for that welcome. I think what's really key is that I'm a member of a team that's delivering this project. I'm but a small cog. It's a massive team, it's a massive project, but it's a very powerful engineering team, and we are taking this to the next stage.
Sorry, we need to look this up.
Sorry, thank you.
Where'd it go? There we go.
Okay, so we are talking about nuclear waste and nuclear waste conditioning, disposal, termination. Quite often this discussion comes a little bit too late or quite a bit down the track in terms of the discussion about nuclear. But this is what ANSTO Synroc passion is. It's what we're very interested in. It's what gets us up in the morning. And waste management or nuclear waste is our opportunity. That's what we see it as. What we do in terms of Synroc is we look at the waste, we look at the chemical, physical, radiological properties of that waste. We look at tailoring additives so that when we process it, we can produce a product, a solid, stable product that can be disposed in a geological repository for the required timeline. So we have specific product requirements that we need to achieve. And that's what we are really focused on. My part of that is in Wasteform Design. It's looking at the chemistry of the waste and trying to find the best product that will pass the required product requirements. I'll acknowledge my two co-authors to this talk. Rowan Holmes is our lead process engineer. So he is really in charge of delivering the project or the process, the Synroc process. I'm in charge of the wasteform, he's in charge of the process, but we are intimately engaged. And also Jerry Triani, who is our technical director. So just a brief outline what we'll talk about. I'll give a very brief overview of ANSTO Synroc, bring it into context of what it is. We'll talk about A&M, that's ANSTO Nuclear Medicine, and what the SIMO facility is. I'm already throwing a lot of acronyms around. I'm apologising for that, but I'll explain them. And I'll actually talk about the Synroc process technology. So this is our vision, to be the world's #1 solution provider for the immobilisation and termination of intractable nuclear wastes. And that word is very key. When I asked Dr. A.D. Patterson, our CEO, who gave us this vision about that and word intractable, he said to me, because that basically means impossible to treat, he said, well, what's impossible for someone else is not impossible for Synroc, and that's really true. I think what we're saying here is that Synroc technology is very important. We're not necessarily trying to compete with vitrification and glass. What we're saying is there's a variety of nuclear wastes out there. Vitrification and glass can treat some of those, but there's so many that it can't, and that's the ones that we are targeting. So that's really our story and what our vision is. So very brief about ANSTO Synroc in terms of the wasteform design. You're probably quite familiar with it. It's been around for a long time, since the late 70s, when Ted Ringwood conceived of this concept of using mineral phases to incorporate the nuclear waste radioisotopes. So this is the difference, was the idea that you could take mineral phases that naturally occur in the Earth's crust that have demonstrated their survival for many hundreds of thousands of years, and we can replace some of those some of those ions with radioisotope ions and incorporate them into the structure with strong inorganic bonds. And Ted Ringwood developed this suite of titanate phases, which when you put them together, you could incorporate pretty much the periodic table, all of those elements that you might see at a reprocessing facility. And that was the original Synroc concept. As time has progressed, we haven't restricted ourselves to these Synroc, these titanate ceramics. We've actually involved the waste form and evolved it into other forms as well. So for example, if you're looking at a high actinide waste, you would up a certain part of that ceramic composition, or if you're looking at an actinide waste with other processing chemicals, you might add glass. So we've got ourselves into different forms of a product, for example, ceramics, glass ceramics, or even glasses. So we are not tied to the ceramic compositions that we had back in the early 80s. We've actually developed that into a lot more range of different types of waste formulations. But what is key, and is key to the technology, is the fact that we use the hot isostatic press. So this is where we go back to Mother Nature. Mother Nature uses pressure and temperature to form these phases in the Earth's crust. So we do the same thing. We're using pressure and temperature in our hot isostatic press to form these phases, and that forms our final consolidation step. And what's really key about this is our difference to vitrification, for example. Vitrification is an open melter. So we get a lot of volatilization coming off the top of that melter. So in places that are using vitrification for their nuclear waste, such as in France and the US, they have a vast off-gas system that they need to then treat as well. What we're doing is we're forming a powdered product, a homogeneous powdered product of the right chemistry that we can put inside what we call a hot isostatic press can or a HIP can. We seal that, and then our final high temperature consolidation is done inside the can where we have no volatilization. So there's no need for that additional off-gas system. We don't have the secondary gases. This is a huge advancement in waste management. There's other advantages to HIPPing. It's very versatile. We can use it to produce a range of different waste forms. I mentioned ceramics, glasses, and glass ceramics. We're getting significant volume reduction, and we'll see an example of that as we go on. And we're getting a high density at minimal temperature, and there's some material science advantages with that as well. So let's define what SIMO is. So we've had a lot of success over the last 20 or 30 years, and when I say success, we are very, very well received in the publications and research, and we have a very strong scientific basis. We're well understood around the world. And we've also been the technology of choice for a lot of competitive waste treatment solutions that have occurred over the last 20, 30 years. So example, there's been some processes in the US and the UK where they've looked at some certain waste and they said, what's the best technology for this waste? Synroc's put a bid in and it's been the technology of choice. But for some reason, that could be a political reason, for example, or a change in mindset on that waste, we've never progressed past the research and development, the strong literature base into the industrial facility. So what we've now been given the opportunity to do with our molybdenum waste, so we produce radiopharmaceuticals on site, we have a waste associated with that, we're going to treat that waste, we are now able to move across the technology readiness levels and mature our technology from where we were, which was more a laboratory or demonstration, into industrial facility, through cold commissioning and hot commissioning to an actual industrial plant. So that is what the SIMO project is about. It's about taking the Synroc technology through to industrialization, which we believe will be a game changer in nuclear waste management. So what are we doing? We're taking our liquid waste from Moly-99 production. We are adding some additives and we're solidifying that into a homogeneous solid powder. And then we're putting that inside a HIP can, and then that undergoes high temperature pressure to consolidate it into a final wasteform product that is suitable for disposal. This is a really good comparison because it shows for the amount of waste that we actually produce with the A&M facility. So if we're talking 5 cubic meters per year, for example, of waste from A&M, if we were to try and cement that with a competing technology, for example, that's the sort of volume we'd end up with, 112 cubic meters of cementitious waste. The important thing I'll mention about that cementitious waste, it's solidification. So you've solidified your waste, you've eliminated some of the risk with having a liquid waste, but that cement material may not be, or we would suggest is not suitable for final disposal. If you were to undergo some durability assessment on that cement, the cesium content of that waste would simply leach out. So what we're doing is we're forming a product where we would consider it terminated, it's disposable. We're forming a product that we can put into a geological repository, and in doing so we're actually reducing significantly the amount of waste product we're forming. So that's quite a powerful image there of what we're actually doing in our SIMO project, or SIMO treatment plant. So a little bit about the waste. In the moly production process, we take uranium aluminium target plates. They are irradiated in our opal reactor. They are then transferred in a transport cask to the A&M facility, where they go into a dissolver. And in that dissolver, we add a highly caustic solution of sodium hydroxide, and that precipitates the uranium out, and it also dissolves everything else. Molybdenum-99 is removed from that liquid waste, and then that waste stream is the waste stream we are dealing with. So what we've got in that waste is a very high amount of sodium and aluminium. For me, that's a problem. As a wasteform designer, I need to immobilize that sodium and aluminium, particularly given the solubility of sodium. I need to consider that. In terms of a processing, the concern is more about radioactivity, of course. So the design basis for the Synroc facility is to treat that alkaline waste from Moly-99 production. where we're targeted around about 4,500 litres per annum of waste to treat, plus to treat our legacy alkaline waste as well, which we already have on site. The waste form is tailored for disposal, so we're not looking just to solidify this material and think about something to do with it later. We're actually terminating that waste. And we're also looking for a process that operates safely, reliably, and can be maintained. In terms of the wasteform design, it's really important for us to have a high waste loading. We want as much solid material or as much waste material in our solid wasteform as we can get. But bearing in mind that as we up our waste loading, our performance is going to drop, so our durability performance is going to drop, so there's a balance there. So we're trying to maximise our waste loading, but also guarantee the durability of the product. We also need to be able to accommodate the variations in the waste. So we have to understand our waste, we have to understand the variations of the waste, and design the waste form to be able to cope with those variations. And what's really key is we don't want to produce secondary wastes. And we'll talk a little bit more about that in a minute. So this is a process flow diagram for the SIMO facility. We've got a waste input that goes into the facility. We have a single additive input as well that goes into the facility. The first step of that process is to produce a powder, a free-flowing powder through the facility that we can then fill up hot isostatic pressing cans. It's important to say that the front end, that powder production part of the process, is a continuous process. We're continually feeding waste and additives, and we're continually producing powder at the end. But where we produce our hip cans, then we move to a more batch process. So the hip can is disconnected from the powder processing part of the plant. We seal that can, we evacuate it, and we seal that can, and that can then moves into our hot isostatic press for the final consolidation. And this is an image of some example hot isostatic pressing cans that we have. There's some mechanical design, obviously, that goes into these cans. I tend to work in the laboratory at the very small scale, so the sort of bottom right here. You've got an unpressed can and a pressed can that is folded together. And then Rowan, the process engineer, and his team have worked up to a more 30-litre style size can, which is the big one sitting in the back, which when you hot isostatically press, that collapses down and folds down very neatly to a right cylinder to allow very tight packing in a repository, because obviously repository space is very important to us. So this project, the SIMO project, is phase 2 to the overall A&M project. I think it's really important to say how forward-thinking we are, and we've been in Australia, because we've said, okay, we're going to have an A&M facility, but not only that, we're going to treat the waste. So we're building in the waste treatment with the processing. So we're looking for sustainability here. Eyes are on us, because other people are now saying, other regulators are seeing what we're doing, and so they're challenging their people as well that want to produce more processes, that you're going to have a waste treatment that goes with that process. So eyes are on us, as I say, and this is really, I think, forward-thinking from Australia to have waste treatment associated with a new facility. In terms of the actual delivery of this project, as I say, I'm a small cog in this project, which gives me the great honour to actually talk about it. But we're talking about ANSTO Synroc technology, but there's all groups across ANSTO that are actually involved in delivering this project. You've got ENCP, the safety systems and reliability, health physics, legal teams, A&M. There's really, it goes across site for the delivery of this project, and that's why I say it's such a massive engineering feat. And I think really what is key, that the key issue that we've faced has been in developing the technology to the next steps. We've never had the project, we've never had the ability to treat waste really that's enabled us to get to the next steps of engineering. So we've been in that research and development for 20 to 30 years. We are very well established, but having a waste to put our hands on and to actually treat has enabled us to move into the next levels of the technology readiness scale. Which is not to say that the early levels aren't as important to us, because we are very much a balance, and we're really seeing as we've gone along with this project how intimately involved you have to be in the different parts of the technology readiness scale to bring in those different aspects. Key to the delivery has been our what we call the ANSTO Synroc demonstration plant, this middle picture, which is our engineering facility. This is a one-to-one equivalent of what the final plant will look like. It's fully integrated, but it's a white demonstration facility. So no active material comes through this facility, but what it is now, it's a training bed for operators. It's allowed us to demonstrate the process technology in an integrated way, and it's also enabled us to define the engineering boundaries on the process. So we understand our input waste, and now we can define the engineering boundaries that processes the material. I think an important aspect that we need to say in that respect is we do not cut up our product at the end of it and test it. We're not doing that. We're talking about a radioactive product that we need to quality assure. So our whole process is about quality assurance. We need to know a lot about the input material, so the waste. We need to know a lot about our additives, and we need to guarantee through our processing that our product is going to fall within the required bounds of the product performance. In terms of the differentiators, this is a little bit different to projects that we've typically delivered. This project is about in-house design. We are an ANSTO in charge of the design, so that's a very important differentiator. We've demonstrated the process, so we've been able to increase the technology maturity through process demonstration and integration, which has been really important. Another key aspect to the design is about minimal operator handling or interventions. We're designing to that. We're also designing to auto recovery. So it's all about making your plant, if required, fail safely, and high degrees of automation. That's really important to the design. Okay, I'm just about to finish. Just in terms of outcomes for SIMO, we are going to have a demonstrated facility. We're going to have a plant, the first of a kind Synroc waste treatment plant, and I think that's going to really open up a lot of doors for us internationally once we've achieved that. But probably as important is we're developing the next generation of young nuclear engineers that are coming through and are working hard on this project as well. I'll just finish off by saying that we are in construction mode. We're building the building. The building is due to be handed over to us sort of towards the end of next year, at which case we will go into the implementation of the process. We'll be embedding the process in the facility and then going through hot and cold commissioning. I'll thank the ANSTO Synroc team itself. This is the ANSTO Synroc team, but there's of course a lot more people involved in the SIMO project. And I'm going to take this opportunity as well just to mention Dr. Lou Vance, who has been an integral member, I'm sure is known to many of you. He's been an absolute integral member of the Synroc team for 30, 40 years, and he unfortunately passed away earlier this year, but without him, his expertise and his input, we wouldn't be where we are. So I just wanted to acknowledge him, and with that I'll say thank you for your time.
That was a great talk.
Thank you.
If we have time probably for one quick question, if we have one. Yes?
Hi Dan.
Hi.
I was just wondering, I've always wondered why the hip cans, thank you. I've always wondered why the hip cans are round if you've got to store them in a repository. Is the round design so as when you pack them closely together you've got a little bit of air gap between them and there's circulation? Because couldn't they be like hexagonal or something so they're packing more closely?
So this comes down to being able to collapse and being able to collapse very uniformly every time. Mm-hmm. And it's also, the hip can is also tailored to the wasteform design. So if we're talking ceramic versus glass, they also collapse very differently. So the roundness is about being able to collapse very uniformly without it sticking out and that kind of thing. So, yeah.
Thank you.
Okay.